We are starting with the problem. So now here we will see the application of this topic. That how can you determine the response of the system? So let's say the free vibration test is conducted on an empty elevated water tank, and a cable which is attached to it applies a lateral force of 16.4 kips and pulls tank horizontally by 2 inches. The cable is suddenly cut and resulting free vibration is recorded at the end of the complete cycle. The time taken is 2 seconds and the amplitude is 1 inch. You are required to compute the damping ratio, natural period of undamped vibration, stiffness, weight, damping coefficient, and the number of cycles required to reach the amplitude equal to 0.2 inch. So a tank which is vibrated by certain force, we want to see that how much cycles are required to reach the amplitude 0.2 inch. What is the other properties of the system? So how we will solve this problem? First note down the data of the problem. What is the data given for the problem? The force is equal to 16.4 kips. We know that the zeta is equal to 1 over 2 pi into the total number of the vibrations, because this system vibrates into the 4 number of cycles. After 4 number of cycles it reaches 2 inches, and after 4 cycles in 2 seconds it take the time to reach it 1 inch. So we can determine the value of the zeta. So zeta is equal to 1 over 2 pi L into the log of un over un plus L. Total vibrations are 4. Total vibrations are 4 in this problem. Time required, the first vibration un is, let's say, 2 inches, and the last vibration un plus L is 1 inch. So time to complete the one vibration, damped vibration in this case, is 2/4, because the total time needed was the 2 seconds. The total time needed is also 2 seconds divided by the number of vibrations are 4. So it is 0.5 second for one vibration time period. Now we know that zeta is equal to, today we prove that it is 1 over 2 pi L, as we prove it last, 1 over 2 pi n log of first to the last one. Zeta is equal to 1 over 2 pi n log of first to the last one vibrations. So this slide was missed. So the number of cycles in which the amplitude will decay to half its value at the beginning is given by this. We can also compute by that how much time is needed that the amplitude will reduce by half. For example, if the y is on the y-axis, there is a amplitude, and on the x-axis the damping ratio. So if the damping ratio is reducing,
is
yes. So it is reducing the total half of its value at the beginning is given by this. Let's say the beginning value of the amplitude was 5 inches, and you want to know that how many cycles are needed to make it equal to the half of this amplitude. So you can also get by formula 1 over delta into the log of the 2, and it is 0.11 over zeta. So it's easy. If you know the damping ratio, you can compute the number of cycles required. This is on the y-axis, the number of cycles required to reduce it to the half of its initial value. So similarly, if you want to compute the, you know the first amplitude, and you have the n number of amplitude, you can get the number of cycle. As in this problem we are doing, we can get this. We have the first value, let's say 2 pi L is the first value, or 2 pi n, and let's say you are interested in n plus L, or n plus length of the period is, let's say, so we are interested in that how much is the, from this we can get the damping ratio, so is equal to 1 over, we have the 2 into pi L is 4, number of total cycles multiplied by the log of un. Un is, let's say the first vibration was 2 inches and the last comes out to be 1 inches. Now we can compute from it the value of the zeta. So it comes out to be about 2.76%. In this way, we are able to compute the different parameters for this problem. This problem was first thing to compute the damping ratio, then the natural period. Natural period is the damped period. So total time required divided by the number of vibrations, it is 4. Then comes out to be the stiffness, weight and damping coefficient. So what is the stiffness? We know that the stiffness is force is equal to K times X. So this time K can be determined by F by X. And the force applied was 16.4 and the displacement was 2 inches. So it means that it is 8.2 kips per inch. Then the weight, next is the weight. Weight is equal to mg, whereas m is also unknown. So m is equal to omega is equal to k over m. So omega equal to k by m, and from there you can determine the m as equal to m is equal to k omega square, k over omega square. Case to part 2. This we can compute the value of the m, and omega is also equal to 2 pi over t. Omega is also equal to 2 into pi t. That comes out to be 12.57 radian per second. So mass can be determined by putting the value of omega. The mass can be determined mass as equal to 0.0 k over omega square. So 8.2 by 12.57 square. That comes out to be 0.0518 kips second square per inch. Now you can compute the value of zeta. because the damping ratio damping coefficient ratio was already known. We know that zeta under damped system, it is C over 2m omega. So this implies that C is equal to, from here the C can be computed as 2m omega zeta. So 2 multiplied by the omega it comes out to be 0.036. This is the damping ratio. And you can also compute that how many cycles are needed. Again, the last one, the cycles needed to reach the amplitude to 0.2 inch. So same equation, the first one, the cycles needed to reduce to amplitude, the amplitude, because amplitude goes in 1 inch in 4 cycles. So how much it is needed to reduce to 0.2 inches? So again you can write it as the first equation, this one, and you can say that this is the value to 2 pi into L. This is unknown now, the number of cycles needed to reduce that into log of. You just know that 2 we want to go from 2 to 0.2. N can be determined from here. So that is about 13 cycles. So in this way we can determine the different things, that 13 cycles are needed to reduce the amplitude of the structural system to this value. This was the problem that we solved. Now the one more problem. What is the ratio of the successive amplitude vibration if damping ratio is known? How can we determine the successive amplitude of vibration? So for that we will use this formula. We know that the successive ratio, this is delta. So delta that we studied is zeta over 1 minus zeta square for a high damping value. For high damping value, we use this formula delta Can you see the delta in the symbol?
नो सर, वो यहाँ पे नहीं होगा। सर ये प्रीवियस में था, लास्ट लाइन में।
इसको ले ले, जो हमने इधर भी यूज किया ना सर। We know that the delta is equal to this one, and when the pi go to the other side, the delta is also proved that it is equal to zeta over 1 minus zeta square. When the normally the delta is 2 pi zeta, but when the zeta is large value, then delta is 2 pi zeta over 1 minus zeta square. And it is also proved today that it is equal to 1 over 2 pi. So we can equate this equation equal to 1 over 2 pi, or 2 pi is log of un over un plus L. Now we can solve it. We can write it as 2 pi zeta over 1 minus zeta square should be equal to 1/2 pi into log of un/un plus L. N plus 1. And by taking the on both sides now this equation log of this delta, which is equal to zeta square or zeta, we can take the anti-log on both of side. By taking the anti-log, this equation will be e raised to power this factor exponent is equal to now un, because due to the anti-log the e log is cancelled, so un/un plus 1. This can be written like that. E raised to power 2 pi comes on that side. So from this equation, you can determine now just which is unknown. The unknown, the zeta is given, and you can determine the ratio of the successful ratio of the amplitude is on the right hand side. So this is unknown. This is unknown. And zeta is known. So by taking the exponent power e raised to power 2 pi zeta or 1 minus zeta square, you can determine the amplitude of vibration. Let's say for zeta is equal to 0.01, the answer comes un/un plus 1 will be 1.064 and so on. For second it is 1.369 and for third it is larger value. So as you are increasing the damping ratio, our ratio of amplitude is increasing. In this way you can determine the ratio of the successful amplitude. So we can have a break and then we will continue with the problem. Okay?
Yes, sir.
यस सर.
सर कब ब्रेक खत्म होगी?
बस थोड़ा 15-20 मिनट में कर खत्म.
सर क्वेश्चंस ब्रेक के बाद पूछ लें.
नहीं, आप पूछ लें.